Hmm. Okay, let's get started. This is lecture 5 of our semester. Mm, Today we will talk about mainly on something on doping. Mm, So this is the last slide we have used in our previous lecture. So previously we have introduced the concept of effective dose, and density of state is actually regarded as energy density of number on our electronic states. However, in this case, this effective dose, something like NC or NV, that is actually not a quantity per electron volt. So because it is already integrated over our energy range, so this is actually in a unit of per centimeter, cubic centimeter. So anyway, once we understand this one, then we can express our electron density as this form. So here we have effective density of state, and this is an approximate form of our distribution function. So you know that if we have only this term, it can be regarded as just Maxwell Boltzmann distribution function, where its energy level is given as EC and its Fermi level is given by E sub F. So you can easily understand this is nothing but just Boltzmann's distribution function, and this is the density, integrated density of state. So it will give us a certain information about electron density. It can be roughly regarded as this way. So here we have a particular axis corresponding to our energy, and all over our electronic states are just concentrated at an energy called as E equal to E sub C. That is the minimum energy of our conduction band, and we are asking ourselves what is the distribution function at that point. So this question can be well answered by the existence of a certain E sub F. When we have a certain formula, then the distance between EC and EF actually just determines the distribution function. So it is written here. So in reality, our conduction band states are not concentrated at this EC, so conduction band minimum point, but it is highly distributed. But by assuming certain temperature, then we can also expect such kind of distribution function. So at a given temperature, we can define this N sub C. So please note that once again, this is a function of temperature. So we have a strong temperature dependence on this N sub C. Of course, for other quantity, a dual quantity called as N sub V, so valence band effective density of a state. So it has a similar form. However, please note that here we have a different signs for our exponential term. So previously in this electron expression, if we have high, so sorry about this. Okay, so I think that the pencil is stuck. Okay, so now, okay, so when we have this electronic expression, so actually electron density is increasing when we have higher Fermi level. However, that means that for the case of our holes, actually we have to have lower number of holes when we have a higher Fermi level. So that's the reason why here we have different sign. This sign and this sign are different. Well, now let's go to the next one. So this is one expression. So by the way, although we can write it down in that way, it is already quite much approximated one. What we have to do in a most rigorous way is just to, even at equilibrium, we must integrate density of state times our Fermi-Dirac distribution function over our energy range. That should be done. However, if we introduce certain approximations for these quantities, for example, Maxwell-Boltzmann distribution is understood, and certain kind of energy dependence, so like E minus EC and its square root, when those kind of approximations are assumed, then we can arrive at this simplified expression. So, however, in many cases we will just rely on this expression. And now we introduce intrinsic carrier density. So intrinsic means that we don't introduce any kind of impurities in it. So perfect, really perfect silicon crystal. In this case, we have the same number of electrons and same number of holes in conduction band and valence band respectively. It is because here we have EC and EV, and there is no other ways to provide conduction band electron in this case. No, here so here we have originally an electron occupying the valence band state, and when it is summarily excited, then we can have this kind of electron, and there will be certain empty space previously occupied by this electron. So in this case, actually, if we have one electron in the conduction band, then it means that there is one also empty state originated from this transition of an electron from valence band state to the conduction band state. So now we can say that electron density equal to the hole density. So you know that there is another way to provide some conduction band electrons. So the reason why we have same electron density and hole density is since our electrons are provided from the conduction band. If we have, for example, if we have some other ways, other source of providing electrons into the conduction band, then there is no guarantee that the equivalence between electron density and hole density. So let's say that here I have a certain amount of money, something, and I give it to him. Then let's just count the balance between the change of money. So I lost some certain amount of money, and he gets exactly the same amount of money. Good. However, now let's consider not only this two-person relation, but say three-person relation. And instead of myself, but let's say that she gave him to certain same amount of money. Then what will happen? Although I have no change in my pocket money, but he will gain certain amount of money. That is the situation we are considering when the third party appears in this scene. But why now? Intrinsic carrier density, when we consider intrinsic material, there is no other way to provide the electrons. So that's the reason why we must assume the equivalence between electron density and hole density. So in this case, electron density and hole density should be equal. So the left hand side just to express the expression for our electrons, and right hand side we have a whole expression. And let's say now NC is a given number at given temperature, for example 300 Kelvin. Yes, this is a given number, and this is a universal constant, and this NV is also a given parameter at given temperature. Yes, universal constant and given temperature. Then the remaining things are, yes, here we have EC, EF, and EV and EF. However, if we say, for example, if we say the valence band level is regarded as, for example, reference value, then now the remaining thing is, what is the distance between EC and EV, and what is the distance between EF and EV. So since this guy is the reference, yes. So previously we had 3 energy levels, but let's say that valence band maximum is the reference energy. Then we are just having 2 remaining quantities. But you know that, the difference between EC and EV. What is it? This is the quantity called as the band gap. So this quantity is for silicon 1.12 electron volt at 300 Kelvin. So now the only thing you have to understand is, in order to satisfy this equilibrium, this intrinsic condition, actually our Fermi level will be adjusted. So if our Fermi level does not satisfy this expression, then what will happen? Then there will be certain excessively large density or high density of electrons, or excessively high density of holes. So that breaks this kind of charge neutrality condition. It is not allowed. So we must solve this equation as a function of what? As a function of Fermi level. Fermi level will be adjusted to satisfy this intrinsic condition. So now we can easily do this job. Then this is the solution we can have. So you know that at intrinsic condition, our Fermi level will be located at this one. Please have a look at this first term. First term is just average between conduction band level and valence band level. So typically this quantity is called as mid-gap energy. So because when you perform this kind of operation, then EC and here you have EV, and this mid-gap just points out just in between these 2 energy levels, and you have something correcting the difference between the NC and NV. So therefore, if we have a slight difference between NC and NV, effective conduction band dose and effective valence band dose, then there will be small amount of difference. So let's have a look at it. So when you calculate this ratio NC over NV, you may find that this is around 2 over 3, larger than 2 and smaller than 3. So you can find that this number is more or less close to just number 1, and only half thermal energy, but it is deviated from the mid-gap energy by approximately half thermal energy. So 300 at 300 Kelvin, thermal energy is just 25 or 26 milli electron volt. So this deviation is relatively so low. So you can see that although we have a slightly different level, but when we just consider the scale of this one, this is the scale of about 1 electron volt, and this difference is just around 10 milli electron volt. So you know this is just around just 1% difference. So in many cases we just believe that intrinsic Fermi level is located at just mid gap. However, there is a slightly different values, and if you go to other materials, then this effect becomes a little bit more severe, because you know silicon has 2 or 3 in this ratio. However, when you go to the gallium arsenide, then you can see that it is more higher difference between NC and MV. So you know. So anyway, this energy level, the energy level when the material is intrinsic, Fermi level when the material is intrinsic is called the intrinsic Fermi level, and it is typically called as E sub I. Now let's just think about this case. Here we have EC and EV. And instead of this intrinsic case, but consider certain extrinsic case. Extrinsic means that this silicon material is no longer perfectly pure. So we have introduced some impurities into it. Then my question is, where do we have actual Fermi level? For example, if we introduce some donors into it, then although our intrinsic Fermi level is located here, but it will be moved into more close to the conduction band level. So if we have an N-type material, then let's say that, for example, this is the exact position of Fermi level. So simply speaking, when you have a certain doping inside your device, then actual Fermi level can be deviated from your intrinsic Fermi level. But we can imagine that what will happen, it is really intrinsic. So although our Fermi level is not actually corresponding to intrinsic Fermi level, but even in that case, we can imagine that there will be certain energy level corresponding to an intrinsic material. This is really not really existing, but we can imagine it. The reason why I'm talking about this quantity is actually this quantity is the reference energy for our later discussion. So say that how can you express certain energy level or position dependent energy state? So in order to for example, let's say in many cases you may have something like I just lost my pencil. In many cases, for example, this is the vertical axis is energy, and this horizontal axis is real space position. So for position wise, later we can see this typical case. So position dependent EC and EV, that is quite a common case, and which level is determined or specified to specify the change of point position wise change of this energy level. Actually, instead of EC, instead of EV, usually what we take is this intrinsic Fermi level. So of course, once you know intrinsic Fermi level, then you can easily reconstruct conduction band energy level and valence band energy level. Why? Because once you have it, then the distance energy difference between this and that is quite close to just a half band gap. And also once we know it, then by going down approximately half band gap, you will see the valence band maximum. The exact value is available. So instead of stick to conduction band level or valence band level, that this is the typical way for representing position dependent energy levels. So are you all with me? So in that sense, I want to add a little bit more discussion. So typically, when we have a certain electrostatic potential, actually our electrostatic potential tensor, sorry about that. So this electrostatic potential is actually pointing out our intrinsic Fermi level. Okay, so this is voltage and this is energy. E sub I is really the intrinsic Fermi level, so this is in an electron volt unit, and potential is volt unit, so we must convert from one quantity to the other quantity. And here we have just charge of our electron, elementary electron. So this is the relation, and there is nothing more. So there is nothing. So simply speaking, in many cases, when you read your textbook, if you go to advanced level, then you will find there occurs electrostatic potential, and in many cases, electrostatic potential actually points out not other quantities but exactly the intrinsic Fermi level of your material. And here we have another discussion. Well, I understand, yes, and in some cases we have a certain system where not only a single material is involved, but two or multiple materials are involved. So for example, typical example in our case is silicon and silicon dioxide. So they are different materials. Or sometimes even more interesting one is silicon germanium. Here we have, and we can imagine many different ways to have hetero structure. So there is one material and there are another material. Then my question is, okay, then how can we express the position dependent variation of energy levels? So here we can think about certain conduction band level and valence band level, or also even inside in this silicon germanium or silicon dioxide. So in the case of silicon dioxide, then we can expect another kind of, sorry about that, so it should be located not here, but it should be located here. Anyway, these red lines just shows the conduction band inside the silicon dioxide and conduction band in silicon, on valence band in silicon and valence band in silicon dioxide. So if we have two different materials and if we consider EC and EV, in reality we must care about four different quantities. So that sometimes that is too tedious. So what we do in this case, even when we have heterogeneous structure, so we just consider the movement of, example, the movement of intrinsic formula. So it's okay. And even in this silicon dioxide, instead of considering the movement or special variation of silicon dioxide's intrinsic formula, we just consider the change of our silicon's intrinsic formula level. That sounds quite weird. So here actually we have a silicon dioxide, so there is no silicon at all. However, when we just consider this kind of quantities, the reference energies for describing the conduction band and valence band, in this case we just take the reference material's intrinsic formula level to specify the reference energy at a given position. So if you cannot understand, please let me know. I will try to repeat this explanation once again. But anyway, then natural question is why we are bothered with such kind of quite difficult notation. For example, why don't you just consider the intrinsic formula level of silicon dioxide itself, and here we have a silicon. So why don't we just adopt material-wise description? The point is, when we have this material-wise description, then there will be certain discontinuity at this point. So think about the interface between silicon and silicon dioxide, and they are quite close to each other, so they are attached. Then even at a given position, we can define two different quantities: the intrinsic formula level of silicon and intrinsic formula level of silicon dioxide, and there is no guarantee that they are coincide. So actually they show certain discontinuity. So that introduces much difficulties in our actual description. So instead of that, in order to make our life easy, usually what we do is just to consider the text reference material. For example, when you have the system based on silicon, then the pure silicon is regarded, or relaxed silicon is regarded as the reference material. Another case, for example, if you have a gallium nitride material, then inside gallium nitride material, you can introduce many different materials based on gallium nitride material system and introducing another aluminum. So then, depending on the composition, your band gap state or band structures can change quite a lot. So point-wise or material-wise description introduces quite much difficulties. So instead of that, if you have gallium nitride-based material, then all of your quantity just follow that of gallium nitride. So simply speaking, just to consider what is the reference material, what is the king of your device, your material system. Then that representative one will be used to specify the potential, electrostatic potential all over its entire system. Okay. So simply speaking, I'm saying this simple expression. Okay. So simply speaking, I'll just read it in that way. Electrostatic potential just points out the intrinsic Fermi level of the reference material that is written here. And in this case, now you can easily understand electron density and hole density is quite low, and this low electron density is called as intrinsic carrier density, N sub I. So in some slides in my other one, sometimes I use in this notation, but in this lecture I will just follow the notation of Professor Tower, so I will just use N sub I. This is nothing related with ice node, just it is intrinsic, and intrinsic carrier density can be expressed as this form. So here NC and NB, both of them just depends on the temperature. Do you remember this expression? NC really depends on the temperature, so you can easily understand NC will have a certain temperature dependence. NC, both of NC and NB follow T 1.5 power, so it will follow 1.5. So intrinsic carrier density really depends on temperature, but I'm just misleading you, because although we have T over 1.5 here, T to the 1.5, but this is not the dominant temperature dependence. So please note that there is the exponential dependence of our intrinsic carrier density. So if we have a different temperature, actually it is varying exponentially. So when you have a look at these graphs, then intrinsic carrier density follows this expression, and here we have a minor temperature dependence, but this exponential one is really important. So simply speaking, if we go to low temperature, then Ni drops exponentially, and when you go to high temperature, then intrinsic carrier density increase also exponentially. So now think about this one. Although we are working with the device operated at 300 Kelvin or similar temperature rate, however, when we actually fabricate this device, usually we apply much higher temperature. For example, 900 Celsius or even higher temperature is applied to our silicon wafer, for example, in order to diffuse our impurities into our silicon substrate. In that case, in such a case, actually it is really difficult to have extrinsic condition. What is the extrinsic condition and intrinsic condition? For example, although I will explain it later, so usually the intrinsic carrier density of silicon at 300 Kelvin is approximately 10 to the 10 per cubic centimeter. Then in this case, doping density like 10 to the 17 per cubic centimeter, really a big deal. However, now think about another case, like our intrinsic carrier density just 10 to the 18 per cubic centimeter. Then what happens? When you introduce 10 to the 17 per cubic centimeter doping density, it can be regarded as just nothing, because basically it has 10 to the 18 electrons in it, but we introduce just 0.1 times more electrons into it, so it can be safely regarded. So now let's come back once again. When you go to higher temperature, actually Ni increase exponentially. So when you do high temperature process, then actually even though we have a certain dopant in it, but in many cases it can be regarded as just an intrinsic material. So if you have attended my previous lecture in the previous last semester, we have thought about process simulation, and at that time we first neglected the doping dependence when we consider higher temperature. That is the reason of such kind of approximation. Anyway, so please have a look at this energy or temperature dependence of intrinsic carrier density. And here we have also very important expression, practically very important expression. So electron density, so let's make a comparison for the expression for electron. Here, when you have a look at this expression, this guy, electron density is expressed as the difference between conduction band minimum and Fermi level. EC minus EF was the input argument for calculating electron density, but sometimes it is more convenient to consider difference between intrinsic Fermi level and Fermi level. So what is the difference? Previously we had the difference between EC and EF, and it is written as EI minus EF. Then obviously you know that in order to have this kind of expression, we must do some manipulation, like EC minus EI plus EI minus EF. So we are now using this one as an input argument of our exponential function. So this quantity will be used to correct the previous expression, and that's the reason why here previously we had NC, but now we have N sub I, intrinsic carrier density. Wow. Note that even when we adopt this kind of expression, E sub I can be expressed as just minus Q times phi electrostatic potential. Please try to adopt this expression into our electron density. Then electron density can be expressed as Ni times exponential, please, here we have minus kBt, and once again minus q phi. So are you with me? Of course we have exponential, another exponential term for Fermi level, but for a while just to forget about it here. Please have a look at this quantity. Then this quantity, without any approximation, we can write down in this way. It is exponential, and here we have a minus sign, they are just cancelled out. Then eventually we have phi over kBt divided by q, and you know it. kBt here, this quantity is typically called as a summer energy, and the quantity divided by this elementary charge q, it is no longer the energy, but this becomes a voltage quantity, and this quantity is now called as summer instead of summer energy. Now it is called as summer voltage. So simply speaking, when we adopt this kind of convention for our electrostatic potential, then electron density can be well written as like this. Electron density is given by Ni times exponential phi over summer voltage, and times, of course, here we have some terms related with EFKBT, but for a while just to forget about it. And following the same expression, we can write down in this case here, hole density is given by n sub I times exponential minus phi over Vt, and here also we have EF over KBT. Important one is here we have the same leading coefficient n sub I, and exactly the opposite dependence, exponential positive phi over Vt and exponential minus phi over Vt. So when they are multiplied to each other, this exponential dependence can be cancelled out exactly. So you can easily understand when we calculate the product between n and p, then actually you will have n sub I squared, and this exponential term will be gone. So now you have this expression, and this expression is valid whenever or whichever you have E sub f. It does not depend on the location of your formula bar. How can you change the formula bar? Even though when you have intrinsic material, extrinsic material, regardless of doping density, at equilibrium, always you have this relation. NP product equal to Ni squared. Of course, we must understand this is not exactly accurate condition, because our starting equation, for example, n equal to Ni exponential something, it is already obtained from certain approximation. The major approximation was what? The expression for distribution function. Although we have to consider exact Fermi-Dirac distribution, but instead of that, we just introduce Maxwell-Boltzmann distribution function, exponentially decaying the energy difference. So yes, this is an approximated form, but it is really useful. So in many cases, we will just rely on this expression. Okay, so do you have any question up to now? Okay, now we have about 30 minutes, so I will try to explain other remaining things related to the doping densities. So yes, please recall that we have 7 times 10 to the 23 electrons per cubic centimeter. So maybe you remember that I have shown a picture about 1 centimeter, and 1 centimeter cubic of pure silicon. That looks quite beautiful. But anyway, inside that small amount of volume, so we have 7 times 10 to the 23 electrons. And you know, at 300 Kelvin, we have just learned that the intrinsic carrier density is about 10 to the 10. So you can easily understand, if you have 7 times 23 electrons, the probability to find it at the probability to find an electron inside the conduction band is given as this small number. So sometimes we just treat it as granted, but let me just give you an example. So here, only among 5 times 10 to the 13 electrons, only 1 electron can be found in the conduction band. That is quite low probability. So now let's just think about here. currently there are 4 alive moon walkers, and we have 8.1 10 to the 9 people on the earth. So it means that only 2 times 10 to the 9 people among 1 is the moonwalker. So therefore, in terms of silicon's electrons, the probability to be located, the conduction band, is much lower than the probability to be a moonwalker. So this is really extremely small probability. However, is it common to every material? For example, if you go to the copper, then actually the number of conduction band electron in the same volume, 1 cubic centimeter, is given as 8.5 times 10 to the 22, even close to 10 to the 23 per cubic centimeter. So therefore, let's try to make a comparison between the conductance. Yes, for intrinsic silicon, we have just 10 to the 10 electrons, and in the case of copper, for same volume, we have approximately 10 to the 12 times, or almost 10 to the 13 times more electrons which can conduct charge. So that's the reason why copper is regarded as really a good conductor, and pure silicon is regarded as an insulator. Of course, there is no pure silicon in reality, but it is regarded as a quite good insulator. So anyway, since it is a good conductor, right now the copper is regarded or has been used as a material for fabricate our VLSI devices. So here you can see that this gold colored line, it is made of copper lines. So right now, where can you find the transistors? Actually, these structures are corresponding to our transistors. Actually, we will spend most of our semester on this structure, but in order to provide certain voltage into it, actually we must apply certain macroscopic structure. For example, you must have a battery, and battery, its tip should be connected to this top point. Once it is connected, then the voltage of your battery is just applied to your transistor in that way. So therefore, this gold colored one, typically called as interconnect, should be a good conductor, and typically we use the copper. So we have been quite happy with copper approximately for 20 years, and now we are getting more and more unhappy with it. So nowadays we are now thinking that we must find an alternative material which can be used instead of copper. It is because, it is also related with our later discussion. So why we don't like copper, or getting more and more unhappier with copper, that is related with this one. Please try to find out your copper in this slide. Please find out copper. Where can you find copper? Oh yes, here you have copper here. this graph just shows what happens when you insert copper impurity into your silicon material. That is written here, and here we have a conduction band level, and here we have valence band level. And for pure silicon, between EC and EV, we have no other electronic states. However, when you introduce copper into it, then actually this copper introduce some electronic states whose energy level are located in between EC and EV. So please concentrate on this copper, then you can easily find that multiple states are generated by insertion of copper impurities into your crystal material. And I wanted to ask you whether these levels are close to EC or close to EV. If we have to select one of them, only one of them, then maybe all of us can answer, okay, the copper introduced levels are closer to the valence band compared with this conduction band. Yes, you are right. However, please try to read the energetic difference between valence band and those levels. Can you read it easily? So to me, it looks like 0.24 electron volt, and this is corresponding to 0.4, and another one is 0.53. Yes, it is a slightly closer than conduction band, but please have a look at this good desirable cases like phosphorus or arsenic or boron. So especially in the case of boron, what is the difference between valence band and boron introduced levels? It is just 44 milli electron volt, and compared with this 44 milli electron volt, this 0.24 electron volt is somewhat larger. Oh, large energetic difference between them. So later we'll see why we have some problems about it. So anyway, now let's come back to this copper. It is certain that when you introduce copper material into your silicon crystal structure, it introduces certain levels, and these levels are located not very close to this valence band, but they are located somewhere far away from EC and EV, and you know they are acting as a killing factor for our VLSI devices, so we don't like it. So please have a look at it. Here we have blue material. It represents our pure silicon. Oh, we love it. We wanted to make it as pure as possible. And here we have gold colored lines. They are interconnect, and it is made of copper. So when they are separated, silicon is working as a semiconductor, and copper is working as a good conductor. Very nice. However, now think about a bad situation, like certain copper material is moving inside our system and eventually enter into the silicon material. Then what will happen? Once it is located inside the silicon, then it can introduce some states located far away from EC and EV. So what will happen? We will see it later, but this is regarded as a very bad situation. So what we have done up to now is, yes, copper is a good material, but here we have a silicon. We wanted to separate it, but unfortunately copper is really good to move, so it is really good to move around this silicon vapor. So that's the reason why for a long time we could not use copper, although everybody understood copper is a good conductor. I wanted to use copper for interconnect, but we could not use it because once you introduce copper, that destroy your silicon wafer. But now, or 20 years ago, people has invented a certain capability or ability to introduce certain barrier material. So this one is not as conductive as copper. However, it is good to prevent the movement of copper. When the copper is just placed on top of this barrier material, then it cannot penetrate into it. So it is just confined on that part. So that's the reason why now copper can be safely confined only in the interconnect line. In the previous case, when your interconnector was large enough, let's say it was good. However, now you have introduced so many advanced technology, and now when you draw it schematically, then actually now our situation is like this with some exaggeration. So now this is copper and this is copper, and we have a barrier material. The role of barrier material is just to prevent the movement of our copper, and it does not contribute quite good conductivity to our interconnect. But now, previously we had a large, wide enough interconnect, and now we have quite much scaled interconnect. The portion of copper, a good conductor, is reduced significantly. So that's the reason why although we are using copper interconnect, but actually it is difficult to find sufficient amount of copper. So that's the reason why we wanted to introduce a different interconnect material. For example, certain research institute say that we must use some noble metals into it. However, usually they cost quite a lot. So I'm afraid that if we just move into this noble materials to make interconnect, then actually we must spend more money to build the interconnect. So I'm not quite sure whether that will be the real research direction or not. Actually, since this is the engineering, not a science, therefore usually the progress or advance of our transistor technology always followed the cheapest available way. So most economic way was the way we have adopted up to now. So therefore we must have a look at. So maybe you will see later what is happening. So anyway, although I have shown you the important application of copper, but all of those kind of discussion was related with this problem, introduce a certain energetic state located in this balanced forbidden zone. So I wanted to discuss about why we have to have this kind of problem in this slide and following slides. Okay. Before starting our discussion, we must talk about this one, dopants, or sometimes we call it as impurities, and we must understand although we have introduced seemingly quite a lot of impurities atoms into our silicon, but compared with the total number of silicon atoms in it, the ratio is quite low. So for example, to me, 5 times 10 to the 20 per cubic centimeter, it is an extremely high density. So that is quite high, quite close to the limit of doping density, upper limit of doping density. But when we just measure the density of silicon atoms, this is just 1% of silicon. So although when you introduce 5 times 10 to the 22, we can, for example, we can just write down, for example, silicon 0.99 and arsenic is just 0.01. But you know that in many cases, in these days, you are using silicon germanium alloys, and typically you have 0.7 germanium 30% or germanium 20%. Those kind of materials are also typically used in our fabrication. So although yes, all of them just share the same property, okay, there is the mother material called as silicon and some impurities are introduced. However, we make a clear distinction between them. When we have this non-negligible amount of second material, then we call it as alloy. And when we have this negligible portion of a second material, then we just treat it as pure silicon where impurities are introduced. You know, then what is the clear cut between alloy and this just doped silicon? There is no such kind of thing. So there is just a smooth transition from doped silicon to an alloy. Okay, so we must understand, actually, although to us this kind of 10 to the 20 seems to be quite high density, but even in that case, from the viewpoint of silicon, this is just a rare event to find an impurity atom. And we can consider two cases. The first case is arsenic, phosphorus, and boron. Please try to find them. Actually, I have introduced different colors, so when you have a look at the red colored one, they are regarded as good material for dopants. So you know that when you have phosphorus and arsenic, then the electronic states introduced by phosphorus or arsenic are quite close to the conduction band. On the other hand, if we introduce boron into our silicon crystal, then it will introduce a state quite close to the valence band. So in this case, they are regarded as good impurities. However, let's have a look at other cases. These ones are regarded as a very representative bad contaminator, not impurity, but they are regarded as bad things which should be avoided from our mass production. So I have introduced green ones, so please have a look at what is the common fact between these materials. When they are introduced, they introduce certain levels which are quite much off from EC and EV. So therefore, that's the reason why. So now we can understand, if a certain impurity introduce a state which is quite close to conduction band or valence band, then it can be used as a good impurity. And if it introduces a deeper state, so whose energy difference is quite high, then they are regarded as contaminators. So of course you can ask me, oh well, we have seemingly some counterexample. Lithium have even shorter energy difference than phosphorus or arsenic. Or here we have antimony, but usually antimony is not used as a dopant. But you know that they have some other properties which is not prepared by our mass production. That's the reason why they are not used as impurities. Okay. Now it is certain that if we have deep state, then they cannot be used as dopants. Okay. Then now let's go to this discussion. Why do we have such kind of a difference when it is close to the conduction band or valence band? It can be used as a good impurities, and why it is not when it has a deeper state? So now let's consider an intrinsic silicon case. Intrinsic silicon case means that now we have different source of electrons. Previously we had conduction band, valence band only. However, now we have another state introduced by our impurity. So now we have such kind of situation. I mean that although our electrons originally located in this EV, under the EV, is not summarily activated. However, there is another source of electrons provided from our impurity level. Then now we can say, although we can have a certain conduction band electron, but since it is not originated from the valence band electrons, so in general there is no guarantee that electron density equal to hole density. So there is no such a condition for extrinsic silicon. However, since electrons are moved from here to there, so if we consider their grand sum between electron in conduction band, and electrons in this impurity level, and also holes in this valence band, then they should be balanced. Are you with me? So now this is not two-party game, but now here we have first party, second party, and the third party. Then their overall sum should be once again conserved. However, now we have introduced the third one corresponding to the trap. So now charge neutrality can be expressed as this way. Charge neutrality means that actually there is no positive charge or no net negative charge inside this system. But this is a little bit confusing when we can express or apply this charge neutrality condition. For example, even at equilibrium case, can we apply the charge neutrality condition to our device? For example, think about this one. You have already studied the p-n junction. Yes, you have a p-n junction, and you can just apply 0 voltage difference between your p-type region and n-type region. Here you have p-type and n-type. Here you have your anode, and here you have your cathode. And let's just connect them without any voltage difference. Then you can understand this p-n junction will be located at the equilibrium case. Then my question is, okay, we have an equilibrium case. Now can we apply the charge neutrality into our system? The answer is no. Think about the depletion reason. Even at equilibrium case, inside the depletion region, your all electrons are gone and your all holes are gone, and there only exist space charges due to the dopants, and they do not satisfy this charge neutrality. Charge neutrality is more related with not this equilibrium condition, but related with homogeneity of your system. Homogeneity means that your system is so large and uniform, and if you introduce certain unbalance, then that will introduce a certain problem. For example, let's think about this one. Now you have a cube 1 centimeter by 1 centimeter by 1 centimeter. You have a silicon cube, and now let's say that your cube is strongly charged. So then what will happen? You have a small silicon cube, but it is charged negatively or positively. Then what will happen? Then it can generate certain electric field all over our system. So it is not, in a macroscopic sense, it is not allowed it. So when you have such kind of thing, then there will be certain reaction to neutralize it. So for this case, if our system is homogeneous, then it is not allowed it to have such kind of charge imbalance. So I mean that, therefore, when you consider charge neutrality, please be careful. Charge neutrality is not a property of equilibrium case. For example, I wanted to say a typical equilibrium property is like this. Yes, here we have certain relation quite much used. However, this quantity is not a property of a homogeneous. I mean that if you have a p-n junction at equilibrium, then even though doping density change everywhere, but everywhere you can use this expression because this is the equilibrium property. However, the charge neutrality is nothing related with that equilibrium condition, or less related with equilibrium condition, but this is more closely related with homogeneity. So of course, if we introduce this charge neutrality condition, simply it means that when we make the point-wise charge sum, that should vanish. There can be positively charged particles, there can be negatively charged particles, and their density should be equal. Then please try to find out positively charged particles and negatively charged particles. What will be the negatively charged particles? I know it. Electron. Yes, electron is negatively charged. And I know a positively charged species. That is hole. Hole is, yes, positively charged. Previously, without any dopant in it, then that was it. So therefore, we had intrinsic condition for our system. However, now we have introduced this kind of impurity level, and when you, for example, now let's consider the donor case. In the case of a donor, then we can think that there is certain amount of donor density. So don't be confused. this ND means that the density of your donor atoms, and they are in this expression, they are all considered as just positively charged. Then now we have to have certain amount of here another electron, but this electron is not occupying, so please let me make a comparison between these two terms. Here we have an electron and another electron, but please, this electron is the usual electron occupying the state in the conduction band. This is the normal electron when we say that electron and electron and electron. And there is a second term. This is the electron occupying not the conduction band state, but the state in the forbidden zone. Yes. Now let me just draw once again, and we are quite close to the end of our lecture. So let me just draw one diagram, and I will wrap up today's lecture. You can find it. Okay, here now here EC and EB. Now we can say that electron density, it is negatively charged, and we have a hole density, it is positively charged, and there is one state generated by our donor, and it can have ND, and this ND is positively charged, and also electrons occupying this new level. So I'm saying that we have 4 different terms. Yes, electron, hole, they are easy, and 2 other terms originated from the ionized atomic core and electrons occupying those states. So the sum of these 4 quantities should be made, and they should be balanced. So that is, although it is written a slightly different manner, but it is corresponding to equation 2.17. So we will continue our discussion in next Wednesday.